Hello everyone! Welcome back to General Math Made Easy with Teacher Joanne. In this video, we are going to learn about the applications of exponential functions. What are the learning objectives? At the end of the lesson, you should be able to represent real-life situations using exponential functions and solve problems involving exponential functions. Where can we apply the concept of exponential functions? The best thing in studying exponential functions is that they have numerous applications to real-life situations. Exponential functions can be applied to quantities that increase or decrease in an amount exponentially. These are the commonly used applications. First, the exponential growth, then we have the exponential decay, then the radioactive decay, and the compound interest. So in this video, we are going to cover each of these applications. Let's begin with exponential growth. Exponential growth is applicable to quantities that tend to grow or increase exponentially and at different rates. The common application of exponential growth are the following. We have the human population, animal population, bacteria, number of virus, and economic growth. To find for the exponential growth, we need to follow this formula. P of t is equal to p sub 0 times 1 plus r raised to t. P of t is called the population at time t, or the exponential growth. P sub 0 is the population or the initial amount at time t equals 0, and r is the rate of growth and t is the time. Let us now have an example. The population of a small island is growing exponentially at a rate of 2% per year. Find the population of the island after 20 years, given that the population is now 70,000. This problem is an example of exponential growth. Is it because of the keyword growing? And to solve this problem, let's first list down the given values. We have the rate, which is at 2% or 0.02. We also have the time, which is 20 years. And the current population, which is 70,000. Following the formula for the exponential growth, we have P of t is equal to p sub 0 times 1 plus r raised to t. So we are looking for the population after 20 years. So we have P of 20 is equal to 70,000 times 1 plus the rate of 0.02 raised to the power of t, which is 20. Simplifying all of this, we have 70,000 times 1.02 raised to 20. So based on this, we have P of 20 is equal to 104,016.32. So it's approximately 104,016. We need to round this off because we do not have 0.32 person. So what can we conclude? At the end of the 20 years, the population will be approximately 104,016. Second problem, Frank started working in a company in year 2004. If the company gives an annual salary increase of 4% and he earned $2,150,000 in year 2019, how much was his starting annual salary? This problem is an example of exponential growth. It is because of the keyword increase. Now, let us list down the given values. First, we can see here a rate of 4% or 0.04. We also have the time, which is from 2004 to 2019, and that gives us 15 years. And then we have the amount after 15 years of 2,150,000. So that gives us the P of 15 So following the formula, we have P of t is equal to P sub 0 times 1 plus r raised to the power of t. Substituting the given values, we have 2,150,000 for the value of P of t, which is P of 15, equals P sub 0, which is the unknown since we're talking about the starting annual salary, times 1 plus the rate, which is 0.04, raised to the value of t, which is 15. Next, we have 2,150,000 equals P sub 0 times 1.04 raised to the power of 15. To solve for the P sub 0, we need to divide both sides by 1.04 raised to the power of 15. Cancel this and divide this 2, so we have the answer of P sub 0 is equal to 1,193,818.68. So what can we conclude? Frank's starting annual salary in 2004 is 1,193,818.68. Under the exponential growth, we have the concept of doubling time. This concept is applicable to exponential growth problems that focus on doubling in number. So the formula to be used here is given by P of t is equal to P sub 0 times 2 raised to the power of t over d, where P of t is a population at time t, P sub 0 is a population at time t equals 0, d is a doubling time, and t is the given time. Here is the example problem. If the number of bacteria in a certain culture doubles every hour, and there are 250 bacteria present initially, find the approximate number of bacteria present after 20 minutes. So here, the keyword is doubles. Therefore, this is under the doubling time. Let us list down the given values. Here, we have the initial number of bacteria, which is given by P sub 0 is equal to 250. We also have the time, which is in 20 minutes. The doubling time, which is every hour. So we have D is equal to 1 hour. But since our time is only in minutes, let us convert the 1 hour to minutes, which is equal to the 60 minutes. You need to make sure that you have the same unit of measurement. Here we are looking for the P of 20 minutes. Therefore, we need to follow the formula. P of t is equal to P sub 0 times 2 raised to the power of t over d. So we have here P of 20 minutes is equal to 250 times 2 raised to the power of 20 over 60. Here we can simplify the exponent. We have 250 times 2 raised to 1/3. By pressing your calculator, here the answer is 314.98. So this is the population of bacteria after 20 minutes. So we can now have the approximate value by rounding this off to 315. So we can now conclude that after 20 minutes, there will be approximately 315 bacteria. The next application is the concept of exponential decay. This is the opposite of the exponential growth. This one is being used for quantities that tend to decrease exponentially and at different rates. So for the formula, we need to follow P of t is equal to P sub 0 times 1 minus r raised to the power of t. If you're going to compare this with the exponential growth, the only difference is that here we have 1 minus r since there is a decrease in value. For our example, A population of 10,000 fruit flies is dying off at a rate of 6% per minute. How many flies will be alive after 15 minutes? Looking at this problem, we have the keyword dying off, which means this is an example of exponential decay. There is a decrease in the number of fruit flies. So first, let us have the given values. We have the initial number of fruit flies, which is P sub 0 is equal to the 10,000 fruit flies. We also have the rate of decrease, which is 6% per minute or 0.06. And we also have the time, which is 15 minutes. Following the formula for exponential decay, we have P of t is equal to P sub 0 times 1 minus r raised to t. So we now have P of 15 is equal to 10,000 times 1 minus 0.06 raised to 15. We have 10,000 times 0.94 raised to 15. Simplifying this, we have an answer of 3,952.92. So this gives us the population of fruit flies after 15 minutes. Since we cannot have a decimal for population, we need to round this off. So this is approximately 3,953. So what is our conclusion? After 15 minutes, there will be approximately 3,953 fruit flies. The next application is the radioactive decay. The common measure of the rate of decay is the half-life of a radioactive substance. It is defined as the time it takes for half of a particular substance to decay. And to solve for this, we need to follow the formula P of t is equal to P sub 0 times 1/2 raised to t over h. Here we have the same variables except for h, which refers to half time. For this example, we have the half-life of a certain radioactive substance is 6 days. The initial sample is 4 grams. What is the amount remaining after 10 days? Looking at this problem, we have the keyword half-life, which means this problem is an example of the radioactive decay. So first, listing down the given values. We have the initial sample of the radioactive substance given by 4 grams. We also have the value of t, or the time we are looking for its amount, and that is after 10 days. And the half time is given by 6 days. Next, we need to follow the formula. So we have P of t is equal to P sub 0 times 1/2 raised to the power of t over h. Substituting the given values, we have P of 10 is equal to 4 times 1/2 raised to 10 over 6. Solving for this, the answer is 1.26. So this is the amount after 10 days. So we can now conclude after 10 days, approximately 1.26 grams of substance remains. The next application is the compound interest. It is defined as interest paid on interest reinvested. What do we mean by this? The interest that has been added to the principal also earns interest. Therefore, the compound interest grows so fast over a period of time. Since the idea here, the interest is being compounded, we need to take note the different compounding periods. So we have annually, which is 1 period in a year, semi-annually, 2 periods, quarterly, 4 periods, monthly, 12 periods. So to solve for a compound interest, we need to follow the formula A is equal to P times 1 plus R over N raised to the power of N times T. P stands for the principal, or the initial amount of investment. A is the final amount, or the future value. R is the annual interest rate. N is the number of times the interest is paid, or which is called the compounding period. and t is the number of years. Following this formula, let us solve this problem. Suppose that 12,700 is invested at an interest rate of 8% compounded quarterly. Find the amount of principal after 6 years. We have the given values. The principal, which is 12,700. The interest rate is at 8% or 0.08. We have the compounding period. Here, it says quarterly, therefore there are 4 quarters in a year. And then we have the value of t, which is 6 years. The next thing to do is to follow the formula. So we have a is equal to p times 1 plus r over n raised to the power of n times t. A, which is the future value, is equal to 12,700 times 1 plus 0.08 over 4 raised to the power of 4 times 6. Computing for this value, we have A is equal to 20,427.15. So what can we conclude? The amount after 6 years will reach 20,427.15. Continuously compounded interest. This is a special case of compound interest. It is defined as the principal is constantly earning interest and the interest keeps earning on the interest earned. This is used to determine the interest earned on an account that is constantly compounded, leading to an infinite amount of compounding periods. So here, to solve for the continuously compounded interest, we have A, which is the final amount of investment, is equal to P, the principal or initial investment, times E, raised to the power of r times t. Here in continuous compounding, it will efficiently reinvest gains continually. In comparison with the compound interest, continuous compounding always generates more interest. In continuous compounding, it is the mathematical limit that compound interest can reach. Example, if 5,000 is invested at 9% interest compounded continuously, what is the investment worth after 8 years? Since it is indicated in a problem that the interest is compounded continuously, we need to follow the formula for continuously compounded interest. So first, let us list down the given values. Here we have the principal value, which is 5,000, the rate, which is 9%, or in decimal, it's 0.09, and the time, which is 8 years. Following the formula, we have A is equal to the principal times E raised to the power of r times t. Substituting all the given values, we have 5,000 times the E raised to the product of 0.09 and 8. This gives us a value of 10,272.70. So this is the amount of money after 8 years. So the investment after 8 years is 10,272.17, having a continuously compounded interest. After discussing the different applications of exponential functions, try to answer the following problems. Problem number 1, you may pause the video to answer this. Let's check our work. The answer here is, the population in the town of Bagong Bayan after 12 years is 164,632. Next problem. The answer here is, there is only 28.14 grams of radioactive isotope. Were you able to answer all of the problems? If yes, great job. Here are the important things that you have to take note about the applications. Exponential functions can be applied to quantities that increase or decrease in an amount exponentially. And there are common applications of this topic. We have the exponential growth, exponential decay, radioactive decay, and compound interest. So here is the end of our discussion about the applications of exponential functions. I hope you have learned something on this video. Don't forget to like and comment on this video. Bye everyone! See you on our next video.